Welcome back, children. In the previous video, we talked about resistances connected in series and parallel, and then we also talked about the energy or dissipated as heat in resistors. And for energy to be dissipated as heat in resistors, then there must be a supply of energy from somewhere else. And one of the sources of energy would be the cells, batteries. I don't mean the biological cells, but I mean the electrochemical cells, and batteries. And we'll talk about the cells and batteries now, and we'll come across a couple of terms there. One is the EMF, and the second one is the internal resistance. We'll do that now. But first of all, the basic distinction between a cell and a battery. A cell is a single unit. Like even in biology, you have a cell as a unit of life, right? So likewise, a cell is a single unit. And a battery is an array of cells. When you connect multiple cells together, then you call that arrangement as battery. So a cell is a single unit. Okay. So that is what you need to remember. So typically, if you take an electrochemical cell, then you can have two types, dry cells and then the wet cells. Will be this one is a dry cell. It's a dry cell, and the cells that you use in remote control instruments, they're all dry cells. But then the car battery is a wet cell. Okay. Anyway, typically, how do you use a battery or a cell in a circuit? It's like this. This is a symbol for a cell. Okay. So the top one is positive, and then the bottom one is negative. The smaller line segment is the negative electrode, and then you have the positive electrode. You represent this. Okay. And then you can connect a resistor here. Okay. So this is the potential of the cell, and then you have the resistor here, and this will drive a current. So this is a cell. And battery is usually a collection of cells like this. So this would be called as a battery. Okay. Again, this will also send a current I. But what does a cell consist of? An electrochemical cell consist of? It basically consists of two electrodes. One would be positive and another would be negative, but then there are two different metals in an electrolyte. Okay, if you take it's typically like this. You have, let's say, I draw a container, and then you have the electrolyte here, and then you have two electrodes. Okay, so this is an electrode, and this is also an electrode. These are metal plates, okay. And this is the electrolyte. So this is an electrolytic cell, and these are two different metals. These electrodes are made of two different metals. So one would be, okay, I'll put this way. This would be, say this is P, this is N, this is positive, this is negative, and say this point here is A, and then this here is B, inside the. Okay. If you take this, there would be a chemical reaction that will be taking place between within this cell. Okay? So actually there is a chemical reaction here and there is also a chemical reaction here. And the result of the chemical reaction is such that the potential of this electrode will be more than the electrolytic solution. And then the potential of this is less than the potential of the electrolytic solution. Okay? So you consider this to be a positive terminal, and then you consider this to be a negative terminal, and then this will be positive. Okay? This is positive with respect to this, and this is negative with respect to this. Okay? Respect to that's negative. Okay. When no current is flowing through it, when no current is flowing through the cell like this, see it's open now. So I have a positive terminal here, and then this is a negative terminal. So when no current is flowing through it, because I have not connected anything to it, right? So there is no current flowing through it. When no current is flowing through it, then the potential of this electrolyte will be the same throughout. Okay, whatever potential this is in and the A is in, B will also be the same potential. Okay. So let us say that I assign a number to it. Okay, this is 0. I say this is 0. And this will be a positive number. This would be a negative number in comparison to that 0. With respect to this potential, it's going to be more positive than this one. It's going to be less positive than this one. So, which means it's negative. Okay. So compare with this. So this is how a cell is arranged. Now, when I connect a resistance across this, like this, when I connect a resistance across this, so what happens now? Then a current will start flowing through that resistor, because you see, you have the positive potential here, negative potential here, and then you're providing a path for the current to flow from positive to negative. So a current will flow through this path, and the current that flows through this resistor I will also flow through this electrolyte. Okay. When the current flows through the electrolyte, then as I said, it is going to experience a resistance. Why? It's natural. We've come across that. When electrons or the ions, when they move, when they'll be colliding with the other ions. So we saw that in conductors. So they will collide and then come back, then collide, come back. So there's some kind of resistance that is offered to the flow of current. And then clearly the exchange of energy will take place, because it is energy, the ions will get accelerated, then they go, then hit the other ions or atoms, and then transfer energy to them, so they will get heated up. So when current is flowing through the battery, then you can sense that the battery getting heated up. Why is it getting heated up? It's because of the collision that is taking place inside when the current flows through the battery. So what you would have is an internal resistance. Okay, there is a resistance, internal resistance. There would be an internal resistance in this. I'll call that as R. Okay, there is an internal resistance when current flows. Small r. It's a very small quantity, but it is still there. Okay? And because of this, you see, the potential will not be the same within the electrolyte. Previously, when the current was not flowing, we said the potential would be the same. Right? But now the current is flowing, and there is a resistance inside, the resistance offered. So the potential will not be the same throughout the electrolyte now. So there will be a potential difference between A and B. Previously VA was equal to VB when no current was flowing. But when current flows, there would be a potential difference between A and B. Okay, just keep it in mind. So clearly, what would be the potential difference between P and N? Okay, so I said previously, when no current was flowing through this was positive. So V plus was the potential with respect to this previously. Okay. And previously again, when current was not flowing, the potential with respect to this was minus V minus, right? Because it's negative potential compared to this. That is how it was. Okay. Now let us see what's going to happen. So this is V plus with respect to this point A, and this is V minus, with respect to this point B. Okay. Now what would be the total potential difference in this path between the two terminals of the battery? You see, there would be a potential difference between this and this, the electrolyte, and then there will be a potential drop between A and B, correct? And then there would be a potential difference again between B and this one, correct? So we are going to take that now. So what is the potential first? Let me take, first of all, potential between Pn is equal to potential difference between P and A plus potential difference between A and B plus potential difference between B and N. So that would be the potential difference between P and N. Okay. So now let us take the first case when no current is flowing through it. When no current is flowing through it, potential difference between A and B is 0. Right, because they are at the same potential. So when no current, what happens? The electrolyte has the same potential throughout. So the potential difference between A and B is 0. So what will happen? So Vpn is equal to potential difference between P and A, the V plus and this part is A. So that is, P and A, that would be V plus. Okay. And what happens here? Potential difference between B and N, that is potential of B with respect to N. What did we have here? Minus V, but that was the potential of N with respect to B, because it was more negative than this. But then what do you want now? The potential of this with respect to N. So that would be the opposite of this, right? So plus minus of this potential, right? So minus of minus V. I hope you understand this. What is this V minus? The potential of this with respect to this. But then when you go this way, then you need to find this potential with respect to that. So that would be negative of that, right? So minus of minus V minus. So that gives you V plus V minus. Okay? This V plus and V minus, when there is no current is flowing, is called as the EMF. E equal V plus V minus. Okay, so what is this E? This E is called as EMF. The expansion of this is electromotive force. So this is abbreviation for this. Electromotive force is abbreviated as EMF. Okay, but it is not a force. This is a potential difference. So this is not going to be measured in newtons. It's not a force. Even though like you're calling it as a force, it's not a force. It is potential difference. So this is in volts or joules per coulomb. So that's a unit for this. Then why do you have this name, electromotive force? That's because of historical reasons. So people, when they were studying cells for the first time, they did not know a lot about force and energy and stuff. So they thought this difference was driving the charges, driving the current. Okay, so they thought it was a force, but it is not a force. It's a potential difference. But that is something that we found out later. But the people who initially came up with this idea of a cell, and then who studied cells and then how cells behaved, thought that it was a force, and then they gave the name EMF, electromotive force, and we are stuck with that name. Okay? But it is not a force, it is potential. It's a potential difference. So the unit of EMF is not Newton, even though you call it as force, it is volts. Okay? So that's it. So this is what is EMF? Like it is the voltage across the terminals of the battery where no current is flowing through it. So when you measure this voltage between the two terminals, the potential difference between the two terminals, where no current is flowing through it, and that value is the EMF. That is what this is capable of. Okay, the battery can give. But what happens when current is flowing in the circuit? I is the current which is flowing in the circuit. Then what happens now? So what happens is that I is flowing here, there will be a potential drop, plus, minus. Okay, and then it comes here. Then here there is a resistance. There would be a plus, minus, a potential drop there. Okay, so what happens here is that this circuit kind of changes into something like this. Previously, I had it like this, right? I had it like this. There is this battery and then this resistor here. So the current I is flowing through it. Now, a better understanding of a cell is this. So you have the cell here, okay, and it will also have an internal resistance R, small r. So the whole thing will become the cell. And these are the ends, the terminals of the battery. Okay, I cannot bypass this. Okay, I cannot bypass this at all because I can connect the resistor only here. I cannot put it inside, right? So I can never bypass the resistor. It won't work that way. So I can connect the resistor only across the two electrodes, the two terminals of a battery. The battery will have an internal resistance and also will have an EMF, as we just saw. So EMF, this is E and then this is R. And then these are the two terminals of the battery, and then you connect resistance R there. Okay? This is a very small number. This resistance is small. The internal resistance of a battery could be a very small number, so you can ignore it in most cases. And compared to R, this will be very small, so you can ignore it in most cases. Okay? But in some cases, you may require it. Okay? But what's the follow-up? Because of this, what is happening? Listen. I is a current flowing through this. Okay? Now you see, as we saw here. So there will be a potential drop here because of the current flowing like this. And then the current is entering here, there is a potential drop across this also within the electrolyte. I told you, the potential drop is not zero. As I said, like the current is flowing, then there would be a potential difference set within the electrolyte. Okay, so note that what would be the potential here then, which is available at the terminal, because that is the only thing which is available to you, right? The potential across the terminals of a cell. I can't put it inside. I cannot bypass R, the internal resistance, the small r. I can only connect my resistance across these two. So what happens now? So what happens now is that if I find this potential, this is what? This is P and this is N. You want to find the potential now, then this part is no longer zero. Potential difference between A and B inside, because IR is a potential drop within that. So what happens now is this. Close the circuit, then this is E, that's EMF here, okay, and then this is going to be is equal to the potential drop across both of them. Or there is something called as Kirchhoff's laws, and we will study about them soon, but I am going to explain a little bit of it now so that we can do it cleanly. Okay. So there are two laws of Kirchhoff's, and then right now we will be focusing on one, the second law. Okay, it's a voltage law, or this is a loop law. So what it says is this: within a loop, a closed circuit, within a closed loop of an electrical circuit, the sum of the potential drops will be equal to 0. That is the second law, the loop law. I'm going to apply that now. So what is the potential drop here? I into R. So I'm entering here, so it's going to be I into this small r. I'll start from here and I'll come back to the same position. So IR is a potential drop here, and then I into capital R is a potential drop here, and then I come here. See, I'm entering it here, plus, here it is minus, so minus E, epsilon is equal to 0. So E is equal to I R plus I R, so that becomes I into R plus R. So I here is equal to EMF by R plus R. Okay? So this is the current. Okay? Now what would be the potential across this terminal? The potential across this terminal will be equal to I into R right now. Okay? When current flows, then what is your VPN? Okay? That is equal to this Vp plus V minus, and also the potential drop due to this, right? Okay, so that would be V plus, and here there is a potential drop. Okay, that is going to be minus I into small r, because this is positive, so this way we are going, right? V plus here, and then we are going this way, so the minus IR, okay, then plus minus of minus V minus. You see, it's no longer 0 here. You will get this part. So that gives you V plus V minus, then minus IR. So VPN is equal to E minus I into R, where I is given by this expression. Okay. So this is E minus IR. Previously, like you had V plus plus V minus, but here that EMF minus IR. So you will get a reduced potential across the terminal when current flows through a cell. When current doesn't flow through the cell, then the voltmeter will read a certain value. That's EMF. Okay? But now the current flows through the cell. When the current flows through the cell, the potential across these two terminals will be less than the one that you measured already. Okay, and that is because of the voltage drop across the internal resistance in the cell. Yeah. So that is what we got here. Vpn is equal to EMF minus IR. Okay, and this can also be written. This can also be equal to I into R. Notice it. Okay, this is a potential difference between these two points, right? So that is E minus IR, or I can write it as just I into R. So this potential must be same as this potential, right? So that can be written also as IR. Okay. There are two ways of writing the same thing. But what you need to understand here is that once current starts flowing in the cell, then the terminal voltage, the voltage available to you at the terminals will be less than the EMF. The reason why it is less than the EMF is because you have an internal resistance within the cell where there would be a potential drop. IR potential drop will happen inside the cell itself. So the terminal voltage will be less than the EMF. Hope it's clear to you. Okay, we have dealt with enough theory now, and let's start doing a problem. I'm taking up example 3.5, and let me read out the problem first, and then we will do it on the board. Example 3.5. A network of resistors is connected to a 16 volt battery with internal resistance of 1 ohm, as shown in figure 3.19. A. Compute the equivalent resistance of the network. B. Obtain the current in each resistor. Then C. Obtain the voltage drops VAB, VBC and VCD. Okay. So here is the circuit. We have this is 4 ohms, this is also 4 ohms, and then it's connected to 1 ohm. Here again I have 12 ohms here, and then 6 ohms here. That's it. So this is a network. Okay. And this network is connected to a battery. Okay. And that battery has an internal resistance of 1 ohm and EMF of 16 volts. So they've drawn like this. This 16 volts and then 1 ohm. Okay. See, they have not given you this dotted box, but I have given you the dotted box because you need to understand that this is the battery. Okay. So this is labeled as A, this point, and this point is labeled as B, and this is labeled as C, and this is labeled as D now. So they want you to find the equivalent resistance of the network. See, when you calculate the equivalent resistance of the network, you should not be including the internal resistance of the battery. Okay? Because you see, what is the objective of finding an equivalent resistance? It is this, right? I want to replace the entire circuit with a single resistor, and then I want to connect it to the same battery, right? Then if I did that, then this must be sending the same current I as it was sending here. So that is actually the equivalent resistance. Okay? So when you calculate the equivalent resistance, you should not be considering this resistor at all, because it is internal to the battery. So this is not part of the network now. I can replace this battery with something else, right? Then the network still remains the same. Okay, so that battery may have a lower resistance, internal resistance. So whenever you find the equivalent resistance of a network, you have to remove the battery and you need to identify those points. And with respect to those points here, the two terminals, you need to find the equivalent resistance. Okay? And the idea of equivalent resistance is this, as I keep saying. That is, if I replace an entire network with a single resistance, the current that I will be sending from my battery must be the same in both cases. That is why you are calculating the internal resistance. You have to think for whom this idea of equivalent resistance would be useful. It is for the guy who supplies power. See, you are a consumer. You are at your home, you are connected to TNEB, and you are receiving power from them. Equivalent resistance may not be all that useful to you. But if you look at the whole thing from the perspective of EB, the Tamil Nadu Electricity Board, then what would they be interested in? Would they be interested in like how many lights you have, or whether you have removed one bulb now, you are not using something? They are not interested in any of those things. They would be interested only in the amount of power they need to send outside. So they have the voltage and they would like to know the current that will go out of their generators. And for that, they will require an equivalent resistance. They will replace the entire the entire place with a single resistance. Your house, my house, and everybody else's house, everything will be replaced with a single resistance. And when that's what they are interested in. So for them, the amount of current which is flowing from their generator is what is important. Okay, and that is why you require equivalent resistance. Okay, anyway, so this is a battery, and so when I calculate the equivalent resistance of the network, I would not consider the resistance of the battery, because that forms part of the source. It is not part of the network. Okay, so equivalent resistance is for the network. Okay, so that said, let us see how to calculate this. Here, okay, these are the 2 points, right? I need to find effective, I have to calculate resistance with respect to these 2 points now. So now you get here, so you see these 2 are in parallel, so I can reduce that. So I'm going to use a different color for that purpose. I can remove these 2 batteries, these 2 resistors, and connect a resistor here. So what would that be? Okay, so that would be, what would be the value of this? So this is my R, right? That's what is my R. So that for AB, okay, I'll call this as RAB. Okay, so 1 by RAB is equal to 1 by 4 plus 1 by 4 is 2 by 4 to 1 by 2. So RAB gives you, RAB is actually 2 ohms. right? So this is actually 2 ohms. Done. Now this is in series, and what should I do now? I need to talk about this. These two are in parallel, so I can remove them and put one resistance. I'll call this as RCD. And what is RCD? So RCD, CMD, right? CMD 1 by RCD is equal to 1 by 12 plus 1 by 6, and that gives you 12, and 2 plus 1, 3, 1 by 4, so that makes it RCD is 4 ohms. Okay. So this is 4 ohms. Now you see 2 ohms is in series with 1 ohm, and that is in series with 4 ohm. So the total resistance of the network, okay, A to D. So the total resistance of the network is actually equal to 2 plus 1 plus 4 is equal to 7 ohms. So that is the equivalent resistance of this network. Okay. This is equal to 7 ohms. 7. Okay. So if I connect, instead of this, if I connect just a 7 ohm resistor across this battery, then the battery will supply the same current as it supplies here. Okay, that's what it is. Anyway, so that's the first part of the problem. What is the second part of the problem? The second part of the problem is this. Obtain the current in each resistor. Okay, so first of all, let's take the current. What's the total current from the battery? So that's easy, right? So what would be the total current? What is I? I is equal to, if I take this, the 7 ohms is the effective resistance, and then you see I have 1 ohm here, right, internal. So total is 8, and then this is 16 volt, correct? So internal resistance of the battery is 1 ohm. The network equivalent is 7 ohms. So they are in series, 7 plus 1, 8, and 16 volts. So the current that's going out is actually 2 ohms. 16 by 7 plus 1 is equal to 2 amps. So 2 amp current is flowing in this. Okay. Now it goes here. You see, it goes here. Then it is going to split like this. So how would it split? That's the question. See, this is the same point, same voltage, right? Same voltage. So what should happen between this point and this point? There will be a potential drop, right? Potential drop here. That is equal to 4. Let me say that this current I splits into I1 and I2. Let's say it splits into I1 and I2. So what do we know? The potential drop between this must be the same. So look at this. So VAB is the same whether you take this path and this path. Right? The potential should be the same here. So VAB must be equal to I1 and then into 4, right? I1 into 4, and it's also equal to I2 into 4. I2 into 4. So all of them must be equal. So I1 4 is equal to I2 4, which means I1 must be equal to I2. Correct? So I1 and I2 are equal. Why? Because I1 into 4, the voltage drop across this resistor is the same as the voltage drop across this resistor. That is also I2 into 4. I1 into 4 is equal to I2 into 4. So I1 and I2 must be the same. But then what happens here? What happens here? What is I? What is I? I here is actually, I splits into I1 and I2. So I is equal to I1 plus I2. And if I1 is equal to I2, then I is equal to 2I1 or 2I2, right? So I is equal to 2I1. But what is I? It's 2 amperes. Then what is I1. So this is 2 is equal to 2I1. So I1 is equal to 1 ampere. Okay. So 1 ampere goes here, and here also 1 ampere was there. Then they combine, then here they become 2 amperes. Okay. Flows here 1 ampere, 1 ampere, then they join here, then they become 2 amperes. So current across this is 1 ampere, this is 1 ampere. Then let's go there. This is 2. So current across the 4 ohm is 1 ampere. Current across this 4 ohm resistor is also 1 ampere. And the current across this 1 ohm resistor is actually 2 amperes. Okay. And what is the current across the 12 ohm resistor? And what's the current across the 6 ohm resistor? That is what you need to find out. So what do we know? Again, VCD. So the potential across these 2 points must be the same whether you take this path or this path. Right? So let's say I comes here again, so 2 amps come here, and let me say this is I3 and this is I4. Okay? I3, that is I4. So I3 plus I4 must be equal to the same I. Okay? So second part is I is equal to I3 plus I4. Then okay, here that is also equal to I2. Okay, 1 ampere. Okay, so here VCD. So here let's say VCD is what? Potential drop across this is I3 into 12 ohms. I3 into 12 or 12 I3 or 12 I3. Okay, and that is also equal to I4 into 6 or 6 I4. Same potential difference. Okay. So what happens now? Then I3 or I4 becomes twice I. So now you have this, right? This gives you 12 I3 is equal to 6 I4. So that gives you I4 is actually 12 by 6 is 2 I3. So I4 is 2 I3. So now can I bring it here? So what is I? I is equal to I3 plus I4. I3 will remain, and for I4 I can take 2 I3. So I say 3 I3 is equal to I. But what is I? 2 amperes. So 3 I3 is equal to 2 amperes. So I3 must be equal to 2 by 3 amperes. Then what about I4? I4 is 2 I3. So 2 into 2, 4 by 3 amperes. So I will say the current through this is actually 4 by 3 amperes. The current through this resistor I3 is 2 by 3 amperes. Okay. So now I got current through all the resistors. Current through this resistor is 4 ohm, 1 ampere, and current through this resistor is 1 ampere. Then here it is 2 amperes, and through that resistor is 2 by 3 amperes, and the current through this resistance is 4 by 3 amperes. Okay, I found the current through all the different resistances. Then what's the question? The third question is obtain the voltage drops VAB, VBC and VCD. I want you to find voltage drop VAB. Okay, I'll go this way. So VAB, and then this is VBC, and then this is VCD. That's easy. What is VAB? I1 into 4 or I1 into 4. Either is fine. So VAB, I1 into 4 or 4 I1. So 4 into what is I1? 1 ampere. Yeah, I1 is actually 1 ampere, right? So into 1, so 4 volts. So this is actually equal to 4 volts. Okay. Then what is VBC? VBC. That is 1 into I2, right? So 1 into I. So 1 into I. So 1 into 2, that is 2 volts. What is this? And what is this? VCD. VCD is either 12 into 2 by 3 or 6 into 4 by 3. Same. Yeah. So that gives you 12. Okay, let's say 12 into I3 or 6 into I4. Either is fine. So 12 into I3 is 2 by 3. So 3 and 4, that is equal to 4 into 8. 8 volts is the drop. Okay? So 8 volt is the drop. So this is here it is 8. It is 8 volts and there it is 2 volts. So you notice 4 plus 2, 6 plus 8, 14. So 14 volts is the drop here. And what about this one? Within the battery, then there is a drop of 2 volts. Why? Because 2 ampere current is flowing through it and 1 ampere, 1 ohm is internal resistance. So 2 volts will drop here, meaning that the potential available outside the two terminals is only 14 volts, not 16. 16 is the EMF of the battery. That is the potential that is available when no current is flowing. But the moment current starts flowing in the circuit, and there is going to be a potential drop inside the battery itself. Inside the battery itself. Okay. So that will reduce what is available at the terminals. You see, only 14 is available from the battery. Even though the battery has 16 volts as EMF, 2 volts will get dropped here. See that, right? 2 amps come here, then 2 into 1 is going to be 2 volts here. So this is going to be plus minus is 2 volts. So this is 16 volts minus 2 volts. So you get 14 volts outside. So it's the same 14 volts here. 4 plus 2, 8. 14, 14. So when you sum it all up, it will become 0. That's the second law, Kirchhoff's law. Okay. So let's see again, let's see like what we've done here. We had a network and then we connected a battery to it. So the first question was to find the equivalent resistance of the network. When you find the equivalent resistance of the network, you would not consider the internal resistance of the battery. Okay. That is part of the battery, not part of the network. Okay. So you are finding the equivalent resistance here. These two are in parallel, so reduce it to 2 ohms. These two are in parallel, then it reduces to 4 ohms. So now 2 ohms in series with 1 ohm, in series with 4 ohm. So total is 7 ohms, and that is the equivalent resistance of the network, and that is connected to this battery. Okay, and when you do that, the battery has 1 ohm resistor and you have 7 ohms for the network, then you can find the total current through this circuit. That is 7 plus 1, 8, 16. So you get 2 amp is the current which is flowing from the battery. So it's 2 ohms is flowing from the battery. And once you find the amount of current, then you see how they are split in these different paths. So the way to do it is, if you take these 2 points, the potential drop must be the same whether you take this path or this path. So you say if it is I1 into 4, it is I2 into 4 again, must be the same. So which means I1 and I2 must be the same. So I1 plus I2 will give you I is 2 amps, I1 is the same as I2, so 1 amp, 1 amp. That's how it splits there. Then here 2 amps flows. Then you come here, then there is again a parallel circuit. Then you can say that I3 flows there, I4 flows here. Then what do you know? Again you take these 2 points, voltage drop across these 2 points along this path must be the same as the voltage drop across those 2 points along that path. So I3 into 12 must be equal to I4 into 6. Using that, we find I3 and I4. Okay? And you find the current in the circuit. And then once you do that, you can find the voltage across the different points that I asked in the third part of the question. So this is how you do this problem. Hope it's clear to you.